Hello everyone, welcome to the lecture on 3D computer vision. And today we are going to talk about 3-view geometry from points and or lines. And hopefully, by the end of today's lecture, you'll be able to derive the trifocal tensor constraint from points, line, or image correspondences of 3 views. And you will be able to describe the homography relations between 2 views. In particular, we'll look at how to derive these homography relations from the trifocal tensor. Next, we'll look at how to extract the 3-view epipoles and epipolar lines from the trifocal tensor. And we'll also look at how to decompose the trifocal tensor into the camera matrices as well as the fundamental matrices that relates the 3 views. Finally, we'll compute the trifocal tensor from image point line correspondences of 3 views. And of course, as usual, I didn't invent any of today's material. I took most of the content from chapter 15 and 16 of Richard Hartley and Andrew Zisserman's textbook Multiview Geometry in Computer Vision, which I strongly encourage every one of you to read these 2 chapters after today's lecture. And if you are interested, please also read chapter 8 of Ma Yi's textbook, An Invitation to 3D Vision. So in the previous lecture, we have learned the fundamental matrix and its role in relating or describing the geometric relations between 2 views. So today we'll look at the trifocal tensor, which is analogous to the fundamental matrix, but it's meant to relate the geometry of 3 different views. In particular, it encapsulates all the geometrical or projective relation between these 3 views that are independent of the scene structure. What this means is that given these 3 views, as long as we know the image correspondences, it could be a point, point, or it could be a mixture of point and lines. For example, we will be able to relate and compute the trifocal tensor of that relates these 3 views, and then we'll be able to decompose this trifocal tensor into the geometric information of camera projection matrices, fundamental matrices, etc. Now, many ways to derive this the trifocal tensor relation. In particular, there are several different combinations of point line image correspondences. So we will look at one particular combination here, which is the line and line correspondences in the 3 views to derive the trifocal tensor. But do take note that this doesn't mean that this is the only way to derive the trifocal tensor. You could also start from other combinations, but it will all end up to be the same relation of the trifocal tensor. And so now, suppose that we are given 3 views where we observe 3 line correspondences here, which we denote as L, L prime, and L prime prime in the respective view. From the previous lecture, we all know that each one of these line in its respective view is going to be back projected to a plane that is represented by this plane over here. And since there are 3 different views which see this the line respectively, what it means is that these 3 different planes that are back projected from the respective view, they are all going to intersect at a unique 3D line in the 3D space, which is shown by this line over here. And we'll make use of this particular relation to derive what we call the trifocal tensor. So what's interesting here is that if we look at 2 views, we'll generally notice that there is no constraint that is being provided by a pair of line correspondences in the respective view. And we can see this pretty clearly because any single line that is observed on the image is going to back project onto as a plane in the 3D world. So if we were to take the pair of images and denote the image correspondences as L and L prime, we can see that basically each one of these back projects to a plane, and we know that in 3D space any 2 planes is always going to intersect at a line. Hence, there is no relation that can be derived, or there's no unique relation that can be derived that relates any two views. But things change when we have a third view, because we know that given a third view where we know that the correspondence to L and L prime, let's denote it as L prime prime over here, it's also going to back project to a plane. And we know that in general, three planes, they don't intersect at a line. And when they do, which is the case here, because we know that L prime and L prime tensors are line correspondences, which means that these three lines, they back project to intersect at a unique line of L in the 3D space. And in this particular case, since there's only a unique intersection in the 3D space, this means that there is a certain constraint that constrain geometrically this three particular views. We will see that this particular constraint is what we call the trifocal tensor. For each image in the three view, we're going to denote the camera matrices in the canonical denotation, as we have seen earlier on in the previous lectures. We will denote the camera matrix of the first view as P identity and 0. This is the canonical representation. What it means is that we are assigning the camera frame to be aligned with the world frame for the first image over here. And then we are going to denote the camera matrix of the second view as P prime, which is obviously a 3 by 4 matrix that we write in this particular way. We write a matrix over here, capital A matrix, which is a 3 by 3 matrix over here, and then we are going to write the last column, which is a 3 by 1 vector over here as lowercase a subscript 4 over here. This denote that this is the fourth column of the camera matrix P prime. And similarly, we are going to denote the third view, the camera matrix of the third view, as P prime prime, and we are going to use a 3 by 4 matrix to denote this P prime prime. And the first 3 by 3 matrix over here, we are going to use the capital B to denote this particular matrix. And the last column, which is a 3 by 1 vector, we are going to use a lowercase b with a subscript 4 that denotes that this is the fourth column in the third camera matrix. And we know that after this denotation, P prime and P prime prime, we can also show lowercase a subscript 4. That means the fourth column of P prime, the second view, and the fourth column of P prime prime from the third view, they represent the epipoles of the second and third view respectively, that arise from the first camera. So let's denote this as P prime and P prime prime. So there's a camera center over here, which we denote as C. What this means is that A4 over here represents the projection of C, the first camera center, onto the second image. And this projection over here is what we call the epipole, that we are going to denote this as E prime. We will show that it's actually given by the fourth column of the second camera projection matrix. And similarly, B4 over here represents the projection of the first camera center onto the third image over here. And this particular guy over here, we are going to denote it as E prime prime, and this is going to be our epipole that is on the third image that arise the camera center of the first camera image over here. And so E prime prime is actually equals to B4, and E prime is actually equals to A. This relation can be easily shown by the following step over here. We know that the first camera center here, it's going to be given by 0, 0, 0, 1, because as what we have mentioned earlier on, we denote the first camera projection matrix in its canonical reference frame, which is identity and 0. This simply means that the camera center is given by 0, 0, 0, 1. And if we were to take the projection of this camera center into the second image, which is going to be P prime, that's given by A, a 3 by 3 matrix, and small a 4. This is a 3 by 1 vector multiplied by 0, 0, 0, 1. We can see that this simply becomes A4, which is equivalent to P prime of C. and that's equivalent to the epipole in the second image that arose from the first image. Similarly, we can also show that this happens for in the third view, where we take the camera projection matrix of B and small b4 over here, and then multiply it by 0.001. We'll see that this gives rise to B4, which is the epipole in the third view. Now, we all know that each image line back projects to become a plane. We already seen in the previous lecture that this back projected plane that arose from the image line, it's given by this particular equation over here, where we denote the plane as pi, and that would be equals to the transpose of the projection matrix multiplied by the image line in homogeneous coordinates. And in this particular case over here, we know the first plane, which is given by this guy over here, which is pi. This it's the back projection of L over here, and this is going to be pi equals to P transpose of L, which is the first line over here. And since we know that P over here, it's the first camera frame which we denote using the canonical representation earlier on as identity and 0, we can see that this gives rise to this particular equation over here. This should be identity. So it's a 3 by 3 identity, and the last column is 0 multiplied by the vector of L, which is a 3 by 1 vector. So this is a transpose. This means that from a 3 by 4 matrix, after a transpose, this becomes a 4 by 3 matrix over here. And after taking the transpose of this guy over here and multiplying it by L, we can see that it gives rise to the plane equation, which is denoted by the first 3 entry would be the image coordinate, and the last entry would be 0. So similarly, we can do the same thing for the second and third plane that is being back projected by the line correspondences in the second and the third view, which is denoted by L prime and L prime prime over here. So here in this figure over here, we can see that L prime is here in the second view. So the back projection here would give rise to pi prime, and that would be equals to P prime transpose multiplied by L prime. So similarly for the third view, this guy over here, the darker shaded plane over here, that's pi prime prime, and that would be given by P prime prime transpose multiplied by L prime prime. And substituting this representation of A and B's over here into the second and third plane equations over here, and we'll end up to have this vector and this vector representing the second and third back projected plane by the line correspondences in the second and third view. What's interesting here is that we know that these three planes, they are not independent because they are formulated, or they arose because of the line correspondences, because L and L prime over here and L prime prime, they are correspondences in the three views. What this means is that pi prime and pi prime prime, the three back projected planes, they are not independent because they have to meet at a single line intersection, which is the 3D line that gives rise to the line correspondences in the three respective images as L prime, and L prime prime. And we also learned in the earlier lectures that this intersection constraint can be algebraically represented by a 4 by 3 matrix, which we call M over here. That would be a 4 by 3 matrix where each column here, it's the respective equation of the planes. This is 4 by 1, this is 4 by 1, and the third guy over here would be also 4 by 1. We simply concatenate them together into a 4 by 3 matrix, which we call M over here. And since we know that these three back projected planes, they are not independent of each other, what this means is that the 4 by 3 matrix has to be rank deficient. We'll show in the next slide that this not just only that is rank deficient, but it has a very precise rank of 2. And now we proceed on to show that the M matrix over here that is formed by the three back projected planes are rank deficient. And we know that this three back projected planes, which we denote as pi pi prime and pi prime prime over here. They have to intersect uniquely at a single line over here, which in the 3D space, which we denote by capital L. And the reason is because this capital L back forward projects to the respective image line correspondence of L, L prime, and L prime prime. This is because L prime, and L prime prime, they are correspondences that is formed by the 3D line. Hence, the matrix that is formed by pi prime and pi prime prime is going to be rank deficient, and the M matrix that's formed by the three back projected planes, it's going to give rise to the intersection. So we all know that from the previous lectures that the intersection of the three back projected planes intersect from at a unique line, and this particular 3D line, which we call L over here, can be represented by all the points that sits on this particular line that we are going to call as X, and we know that X over here can be parameterized by any 2 points on this particular line, because we know 2 points is going to represent a single line that is passing through these 2 points, which we call x1 and x2, and this is going to be parameterized by alpha and beta, which are scalar values here. And we know that this x over here, which represents the points, all the points, the possible points that sits on this particular 3D line, it's going to also sit on the respective plane. So there is an incidence relation between x, this any points that is on this line. It could be anywhere on this line, which we call x over here. It has to have an incidence relation with pi, the first plane, pi prime, the second plane, as well as pi prime prime, which is the third plane over here. Hence, we can write the dot product of the plane and the respective plane with this 3D point over here to be equals to 0. And this holds for all the respective three planes. Hence, we get this equation of pi transpose x equals to 0, pi prime transpose x equals to 0, and pi prime prime transpose x equals to 0. This relation here can be rewritten into M transpose, where M is what we have seen earlier on, is pi prime as well as pi prime prime in the previous slide over here. We can stack them together and put the transpose over here and write x. So this effectively works out to be the respective plane equation dot product with any 3D point that is sitting on this particular line over here, and that would add out to be a vector of 0, 0, 0, which is because each one of these is going to give us a 0, which is shown here, a scalar 0. But concatenating them together as a matrix over here, we're going to get the 3 times of zeros from each one of these respective relation over here. And consequently, because the fact that a point on the line, we saw earlier that it can be parameterized as by 2 separate points, x1 and x2, which is 2 parameters over here, or 2 bases over here that represents this particular 3D point sitting on the 3D line. Hence, what this means is that the matrix M that we have defined earlier on would be of rank 2, because it has a 2-dimensional null space solution, since the x over here can be obtained as a null space vector of the matrix M over here. And we know that essentially any of this equation over here, any of this point x1 or x2 is all going to fulfill all the 3 relation over here. Hence, we can rewrite the solution or the equation, null space equation, into these 2 equations over here, and by substituting x1 into x and x2 into x respectively. Hence, there are a family of 2 individual sets of solutions here. Therefore, we conclude that M over here has a rank of 2. And this intersection constraint that we have seen earlier on, the null space equation here that we have seen earlier on, induces a relation amongst the image line correspondences, which is L, L prime, and L prime prime. So I have mentioned earlier on that this is the correspondence. The reason why this gives rise to the correspondence is that because this equation here, the null space equation here, it must be satisfied when all the three planes intersects at a unique line, and hence once this is satisfied, we can also say that the vice versa is true as well, that the correspondence here, the three correspondences here in the images, it must have a certain relation, and that relation would be that they must intersect at a unique line. They are representing a single unique 3D line in the 3D space. And since the rank of M over here is 2, there must be what it means is that there must be a linear dependence in the column, because we saw earlier on that M, it consists of pi prime and pi prime prime. So this is actually a 4 by 3 matrix. And what this means is that since the rank of M is only equals to 2, which means that this 4 by 3 matrix is a rank deficient matrix. This means that out of the three columns, any two of them can be linearly combined to produce the third column. Hence, there's a linear dependence between its column, which it denotes as M subscript I, where I denotes the column index. And hence, we can this particular relation over here, where we simply choose M1, the first column. It becomes a linear combination of the other two columns in the matrix M over here, which we call M2 and M3. And this would be parameterized by two parameters, which we call alpha and beta. They are both scalar values over here. We have seen earlier on that the equations of the respective back projected planes can be obtained exactly from the line correspondences, as well as the notations, the denotations of the respective camera projection matrices, the entries of the respective camera projection matrices in this form over here. So we can now rewrite M into this particular form over here, which consists of all the line correspondences, the three line correspondences that we have seen earlier on here, and the respective camera projection matrices entries, which we call A and B over here. Now, if we were to plug this back into the equation, we can derive some meaningful constraints over here, and we'll see that in the following slide. So before we do that, one particular observation from the 4 by 3 matrix that we have seen earlier on here is that there's a specific number over here, which is 0. It's always 0 due to the canonical representation of our first camera matrix, which is identity and 0 over here, and as well as the relation that we have earlier on, which we have M1 equals to alpha M2 plus beta M3 over here. Let's rewrite this relation over here. So M1 equals to alpha M2 plus beta M3. So we can make use of the fact that this second row first column over here is always 0. So because we know that this is the first column over here is M1, and the second column here is M2, and the third column here is M3. So what it means is that since we know this particular relation, and we know that M1 here is going to be 0 for this particular row and column over here, we can see that in order for it to be 0, we can actually solve for alpha in terms of the A, B, and L's over here in this particular M matrix over here. So we can see that one of the obvious choice would be to let alpha be equals to some scalar k multiplied by B4 transpose L prime, and beta equals to minus k multiplied by A4 transpose L, and that will fulfill this particular equation, this particular relation over here. Let's take a closer look at this. So in this particular case, because we know M1 here is going to be 0, so if we let alpha over here be B4 transpose L prime prime multiplied by M2. M2 is going to be this guy over here, which is A4 transpose L prime, plus we can see that from the next slide that beta, we are going to fix it at minus A4 transpose L prime, and M3 over here would be 4 transpose L prime over here. Of course, the whole thing has to be multiplied by a scalar k, which is anyways going to be cancelled out because on the left hand side it's going to be equals to 0. We can see that the two terms over here they becomes the same, and but with the negative sign in between. Hence, we show that the right hand side over here it becomes 0, which is consistent with what we have over here, and hence the choice of alpha to be B4 transpose L prime prime and beta to be minus A4 transpose L prime, it's going to fulfill this particular constraint over here based on the observation that the second row first column of the M matrix is always going to be 0 over here. Hence, we can apply this alpha and beta that we have found over here in the first step over here to the top 3 vector of each column. That means that we can apply it to this over here, and we'll get L1 because we know L1 here corresponds to M1, which is this guy over here. Then we can have M2 equals to A transpose L prime, which is this guy over here. So this is basically M2 and this is M1 that we have seen earlier on. So this whole term over here is going to be alpha that we have solved earlier on. We can see that this guy over here, B transpose L prime prime, it's going to be M3. So this guy over here is going to be M3, and A4 transpose L prime is we have computed earlier on to be representing beta over here. So this is going to be beta over here. So notice that the scalar value k can be set to 1. So we can simply set this to 1 over here to get this relation. And we can see that by putting all this together, it will actually fulfill this equation over here, which we have seen earlier on, that this equation it arose from the fact that the rank of M is equals to 2, and thus we can further evaluate this into this relation over here. This guy over here, the L is an image correspondence. We can simply represent this as L1, L2, and L3 over here. So each one of this, the indices, we can simply denote it as Li. And what we are going to do next would be to derive the expression or show an expression of each entry in this particular line over here in terms of this particular equation over here. So we can simply see that what this becomes would be the two sides of the L, L prime prime and L, these two vectors over here from this equation over here. It can be factorized. It can be factorized out. And since we are only interested in any entries over here, since this guy over here is a 3x1 vector over here, we can simply look into A over here and take out a particular column of A here for this dot product over here to become a scalar value. Hence, the whole thing over here can become a scalar value that represents the ith coordinate of the line L. And we can do the same for the second term over here. Then we can see that we can rearrange this because this is a dot product. It doesn't matter on which direction over here. We can simply swap the transpose and swap the place because this is just simply a dot product over here. Now we can see that L prime transpose always appears on the left side of the equation, and L prime prime ends out on the right side of the equation over here. So we can simply factorize this out to get the relation of L prime transpose and then AIB4 transpose minus A4BI transpose L prime prime. So now finally, once we get this particular relation, let's collectively call this term over here Ti. And this is actually a 3x3 matrix. Here we can see from the previous equation over here, by pre-multiplying by L prime and post-multiplying by L prime prime, it actually gives rise to a particular entry in our image line in the first image, L1, L2, and L3. So Li here represents the coordinates of this the first image line over here. So now we can plug this notation back into the equation over here, which gives rise to the what we call the incidence relation. The incidence relation simply means that the three correspondences, they are related by this Ti matrix over here, because we know this was derived from the rank deficiency of the matrix M that tells us that the back projected planes that arose from the three line correspondences must intersect at a single line, which we call L in the 3D space. Hence, this equation over here, it's what we call the incidence relation. And now, we are going to call this set of the three matrices, which is denoted by T1, T2, and T3. Recall that T1, T2, and T3 over here, each one of these, which we generally call Ti over here, it's going to be used to compute the respective entry in the first image line over here. So we're going to collectively call this T1, T2, T3, where each of them is a 3 by 3 matrix over here. So if we were to stack them together, then this becomes what we call the trifocal tensor, because this is a tensor when we stack them all up. So you have a to visualize this, what you see is that this is actually a 3 by 3 matrix which called T1. So imagine that we have another of this matrix of this 3 by 3 matrix that is behind here. So this is T2, and then we have another of this matrix over here which we call T3. So the whole thing forms a 3 by 3 by 3 cube, where T1 is the first block over here, and T2 is the second block over here, and then T3 is the third block over here. So this 3 by 3 by 3, it's in comparison. So if I have just n by 1 dimension, I call this a vector. And if I have two dimensions, I call this a matrix. So now what we have over here is a 3 dimension. So this becomes a tensor. And hence, we call this thing here, the set of three matrices, the trifocal tensor. Because trifocal, because it's used to relate the incidence relation between three image views. Because it's a tensor over here, it's a 3 dimensional matrix, which we can, if you would like to call it that way. So the former term would be a tensor. Hence, we call the whole thing a trifocal tensor. And now we can rewrite the incidence relation into this equation over here, which is actually the same as what we have seen earlier on, but in this case here, it was just meant to be each respective entry in the image line of the first view over here, and we have to denote T using the respective I over here, but we can collectively write them into a square bracket and T1, T2, T3. So this actually represents the tensor or the trifocal tensor over here. It's a 3 by 3 by 3. So by writing this notation, pre-multiplying by L prime transpose and post-multiplying by L prime prime transpose, this actually represents an end result of the vector of which is given by first multiplying by the first block in the trifocal tensor, and then the second block of the trifocal tensor, as well as the third block of trifocal tensor. And these individual operations are simply, or what we simply derive here, using the incidence relation of three views. Although we define the canonical camera notation using the first frame. What this means is that we use the first frame as the reference to derive the trifocal tensor relation that we saw earlier on. And this simply gives rise to this particular relation that we have seen earlier on here. But because we base it on the first view, hence in the equation earlier on, we saw that it's L transpose equals to this L prime transpose Ti multiplied by L prime prime. So if we make use of the second frame as the reference frame, this is what we will get. We will see that the relation swap order, as well as if we use the third frame as the reference frame, we will see that it's going to swap order. The L's are going to swap order. And notice that if we change the reference view, to the second view or the third view. The although it is not just purely the lines over here that swaps order, but we will end up with totally different trifocal tensor over here. And what's interesting here is that actually, because they are still the same three views that and the same three line correspondences that gives rise to the same the line in the 3D space via the intersection of the back projected planes. So what this means is, although by choosing a different reference view, the second, third, or the first view, we will end up with a different trifocal tensor. There is actually a relation between all these three different trifocal tensors, regardless of which view that we chose as the reference view. And they are, although they are distinctive, there is a relation between the three different trifocal tensor. Unfortunately, the relation is not so trivial, so we'll not derive the relation between these three trifocal tensor further, and for the rest of the lecture we'll just focus on one of them. That means that the choice over here would be simple. We'll just choose the first frame as the reference frame and focus on this particular equation of the trifocal tensor that we have derived earlier on. Now, with the trifocal tensor, although it has 27 entries, because it's 3 by 3 by 3, we saw that the trifocal tensor is given by T1, T2, and T3, where each one of this is a 3 by 3 matrix. So there are 9 entries each, and hence altogether there are 27 elements. But the trifocal tensor only has 18 degrees of freedom. We can think of it this way. Each one of the view, it has a single camera matrix which we denote by P, P prime, and P prime prime earlier on. So we also know that from the previous lectures that each camera matrix has altogether 11 degrees of freedom. This is because there are 12 entries. It's a 3 by 4 matrix, and we minus off the scale, so it's 12 minus 1. So it will be 11 degrees of freedom each, because we are saying that three views here, they are supposed to be chosen independently. What it means here is that there are going to be 33 degrees of freedom over here if these reviews are chosen independently. But what's interesting here is that because all these reviews come together, you can think of it this way, where they are actually glued together by the line correspondence that we have seen earlier on. It could be a point correspondence as well, or point line correspondence that we'll see later in the later slides. But so because these image correspondences, they glue the three projection matrices together via the line correspondences, which should back project to three different planes that intersect at the single unique 3D line in the 3D space. This and what it means is that this particular 3D line has 15 degrees of freedom due to the projective plane, because we know that the this thing here, the 3D line L, it can be transformed via the transformation which we call H, and this is actually a 4 by 4 matrix that transform the 4 by 1 that can be applied to transform the 4 by 1 3D line over here. And this has 16 elements in there, but since the scale is not defined, what it means is that we can minus off 1 over here, and that gives rise to 15 degrees of freedom in the projective transformation. So altogether, although the three camera matrices gives rise to 33 degrees of freedom because it has 11 degrees of freedom each, we have to take away 15 degrees of freedom because these three camera views, the three camera projection matrices, they are related, they are glued together by that single line that defines the image correspondences in the three view. So hence altogether we have 18 degrees of freedom, 33 minus 15 for the projective world frame.